Please watch the video entitled The Postulate from Schrodinger. The postulate from Schrodinger tells us we'll predict energy values based on a differential equation. But it doesn't tell us anything about motion, the equations of motion. In order to do that, we need to talk about the time change in a system. In order to talk about the time change in a system, we can come up with the time dependent Schrodinger equation. The first postulate is the time independent Schrodinger equation. So let's go into this, and this will be quick. The math doesn't take that long and it's not that involved. So I hope you still continue to watch this when I go to the drawing board. If these don't look familiar, then you need to go back and watch that video about the first postulate, the time independent Schrodinger equation. Notice there's nothing about time. There's only position. Nothing about time. And when we take the second derivative of position, then since it's not time dependent, this thing goes to zero. This gives us p squared over h bar squared, negative h bar squared, and that's where we get this thing. And of course, this looks like the kinetic energy, potential energy, and here's the total energy. So let's see if we can get some energy related things if we do a time dependent equation. Well, what about this? How about if I take this equation, and to keep things simple, let me just do it this way. I'll take the partial derivative of that function, which we represent with the Greek letter psi, and instead of with respect to x, I'm going to go with respect to time. And what would that equal? It's going to be that function itself times I h bar, and then the derivative of et with respect to t is just going to give me e. Then, of course, I have to include this. Does that make sense? This would be the reciprocal factor of this thing. So if I multiplied this, it would get rid of the e portion. But let's do it this way. I'm going to multiply I over I, which is perfectly okay. That's going to give me negative 1 in the bottom, and that's going to give me negative 1, so that'll be a plus h bar I. Let's see if that works out. That would give me a plus h bar I. And so if I do it this way, let me come up with this approach. I'm going to say h bar I partial derivative of psi with respect to t equals e to the psi. Okay, here's this factor out here. So e to the psi, have trouble saying this Greek letter, but let me just keep going here so I can equate these two together. H bar I, first derivative of psi with respect to t, equals this big long thing, the first postulate, negative h bar squared over 2m second partial derivative of psi with respect to x. And what's left? Plus potential energy times psi. What else do we have? Okay, that's it.